Hey you, ready for a deep dive?
Absolutely. What are we diving into today?
Let's plunge into the world of coordination compounds. I think they're way cooler than they sound.
Oh, I completely agree. They really highlight how teamwork makes the dream work, even at a molecular level.
Okay, I'm intrigued, but before we go any further, can we define what a coordination compound actually is?
Well, think of it like this. A coordination compound has a metal ion at its core.
Like the star of the show.
Exactly. And surrounding that metal ion are other molecules or ions.
Like a posse.
You got it. We call them ligands, and they bond directly to that central metal ion.
So it's like the metal ion is holding court, and the ligands are its loyal subjects.
Yeah, that's a great way to put it. And the number of ligands, what we call the coordination number, is important. It actually dictates the compound structure and its properties.
Okay, so the size of the entourage matters. Are all ligands the same, or do we have a variety show here?
Oh, we definitely have varieties. Some ligands are unidentate, meaning they bond in just one place.
Okay, a single bond? What else?
Then you've got your didentate ligands, which can bond in two places.
Like they have two hands to hold on with.
Exactly. And some ligands are even more clingy, bonding in multiple places. We call those polydentate.
I'm imagining a molecular group hug.
Yeah, pretty much. And these polydentate ligands can get pretty complex, like EDTA with its 6 connection points.
6. That's some serious molecular bonding. Are there any other ligand types we should know about?
Well, there's the ambidentate ligands.
Those sound a bit shady. What makes them different?
They can bond to the metal ion in multiple ways, which leads to something called isomerism.
Isomers. That rings a bell. Are those like molecular twins with different personalities?
You got it. They have the same chemical formula, but their atoms are arranged differently, leading to different properties.
So even a slight change in the seating chart can shake things up.
Absolutely. And we can break down isomerism into 2 main types: structural and stereoisomerism.
Okay, remind me what those are again.
Structural isomerism is where the actual bonds are different. Then we have stereoisomerism, where the bonds are the same, but the spatial arrangement changes things up.
Can you give me a visual for that spatial difference?
Think of 2 square dancers holding hands.
I'm picturing it.
In one scenario, they're right next to each other. That would be a cis isomer.
Okay, side by side.
But they could also be on opposite sides of the square. That would be a trans isomer.
So same connection, different location. I'm starting to see how things can get pretty complex at this level.
Oh, it definitely gets intricate. And these small changes in arrangement have a big impact on the properties of the compound.
Do tell.
Well, one of the most fascinating things about coordination compounds is their color. They can be so vibrant.
Oh yeah, you see that all the time in gemstones, right? The green of an emerald, the red of a ruby.
Wait, are you telling me that gemstones are actually coordination compounds?
Are they?
Many of them are. And those vibrant colors come from the way light interacts with those electrons and the metal ions d orbitals.
Okay, so we've got color, we've got complex structures. How do scientists actually explain the bonds in these compounds?
There are 2 main theories that help us understand: valence bond theory, or VBT, and crystal field theory, or CFT.
Okay, lay those theories on me.
Well, VDT focuses on those atomic orbitals overlapping to create the bonds.
So it's like analyzing each step of the molecular dance.
Exactly. CFT, on the other hand, takes a more big picture approach. It focuses on the electrostatic interactions between the metal ion and those ligands.
So it's about the energy and attraction between the dance partners.
You got it. Each theory has its strengths and limitations.
So like most things in life, it's not about one theory being right or wrong. It's about finding the right tool for the job.
You nailed it. And these theories help us understand why coordination compounds are so important in the real world.
I mean, we've touched on some cool examples already, but let's hear more about how these compounds affect our lives.
Well, let's start with the essentials. Chlorophyll, the green pigment that lets plants perform their photosynthesis magic. That's a coordination compound of magnesium.
Wow, so we're talking about the basis of life here.
And then there's hemoglobin, that protein that carries oxygen in our blood. That's a coordination compound with iron.
Hold on, so we literally wouldn't be here without these compounds.
Pretty much. And that's just the tip of the iceberg. They're also used to purify metals, to treat lead poisoning, even in electroplating.
Okay, mind officially blown. They're like the silent heroes of the chemical world, working behind the scenes to make our lives possible.
You could say that, but the story of coordination compounds goes even deeper. We need to talk about the pioneer who first cracked the code of these molecular partnerships.
Okay, I'm all ears. Who was this chemical Sherlock Holmes?
His name was Alfred Werner, a Swiss chemist who revolutionized our understanding of these compounds in the late 19th century.
So he was the one who deciphered the language of coordination compounds. What did he figure out?
Well, he noticed that sometimes compounds with the same chemical formula behave differently.
That's strange. Why would that be?
Exactly. It was a puzzle, and Werner proposed a radical idea. He said there must be a central metal ion surrounded by a specific number of ligands, forming what we call a coordination sphere.
So he was the first one to see that molecular entourage. Did people buy into his ideas right away?
It was a pretty revolutionary idea at the time, so it took a while for the scientific community to fully embrace it.
But his ideas ultimately prevailed.
They did, and they laid the foundation for modern coordination chemistry. He even introduced this idea of secondary valence, explaining how those neutral molecules could bond to the metal ion.
Okay, so he figured out the bonding puzzle. And how did those different types of ligands we talked about earlier fit into his theory?
Werner realized that the ligands, whether they were ions or molecules, played a huge role in shaping the compound's personality. Different ligands could affect the metal ion's reactivity, its color, even its magnetic properties.
So like with spices, the ligands are adding different flavors to the molecular mix.
Exactly. And Werner's theory gave us a framework for understanding how those different flavors could influence the whole dish.
Okay, I'm starting to get the complexity of this. So we've got this metal ion with its entourage of ligands, all within this coordination sphere. What does that whole structure actually look like?
Picture a bubble surrounding that metal ion, with the ligands attached directly to it. This forms a three-dimensional structure.
Like a molecular dance floor, the metal ion taking center stage.
That's a great way to picture it. And this dance floor has a fancy name, the coordination polyhedron.
Okay, so we're not just talking about atoms, we're talking about shapes.
Absolutely. Some common shapes include octahedral, tetrahedral, and square planar.
It's molecular geometry.
Yeah.
And these shapes, I'm guessing, influence the compound's properties.
Precisely. The shape of that coordination polyhedron is just as important as the arrangement of atoms within a molecule. It affects how the compound behaves.
This is all so fascinating. So we've got these metal ions surrounded by their posse of ligands forming these 3D structures. But how do we communicate all of this? How do we even begin to name these complex compounds?
Well, that's where nomenclature comes in.
Uh-oh, sounds complicated.
It might seem intimidating at first, but it's actually quite logical once you break it down. Just like we have rules for naming other chemical compounds, there's a system for coordination compounds.
Okay, I am ready to learn the secret code.
The first rule, we always name the cation first. Then we name the ligands alphabetically, followed by the metal atom or ion.
So the supporting cast comes before the star.
Exactly. And we have to follow some specific rules when naming those ligands. Anionic ligands get an O ending, while neutral and cationic ligands usually keep their regular names.
Okay, got it. What about the number of ligands? Do we just list them all out?
We use prefixes to keep things tidy, di for 2, tri for 3, and so on.
So if we have 2 chloride ligands, we'd say dichloro.
You got it. And we also need to indicate the oxidation state of the metal ion.
Right, because some metals can have multiple personalities.
Exactly. We use Roman numerals in parentheses after the metal's name. For example, if iron has an oxidation state of +3, we write it as iron 3.
Okay, it's like giving the metal its official title. What happens if the entire complex ion has a negative charge?
That's when the metal gets a special ending, 8. So instead of iron, it becomes ferrate.
It's like a royal designation. Okay, I'm feeling more confident about naming these compounds. What about the formulas? Are those just as complex?
Formulas are actually a bit simpler. We list the central metal atom first, then the ligands, again alphabetically.
So the metal leads the way in the formula.
Exactly. If we have any polyatomic ligands, we enclose those in parentheses, and the entire coordination entity goes within square brackets.
Like putting the whole crew in a little molecular house.
That's a great visual, and of course we always make sure the charges balance out, just like with any chemical formula.
Okay, I'm feeling pretty good about both naming and writing formulas. But let's get back to those isomers. We've covered the 2 main types, but are there even more specialized subcategories within those?
Oh, there are many subtypes of both structural and stereoisomerism, each with its own fascinating quirks.
Okay, let's break it down further, starting with those structural isomers. What are some of the ways those bonds can be rearranged?
Let's start with linkage isomerism. Remember those ambidentate ligands, the ones that can bond through different atoms?
Right, like the ligand has a choice of which hand to use to shake hands with the metal ion.
Exactly. The thiocyanate ligand is a classic example. It can bond through either the sulfur or the nitrogen atom.
So even though the overall formula stays the same, that choice of bonding atom can change the whole compound?
Precisely. Now let's move on to coordination isomerism.
Bring it on.
This one's kind of like a molecular partner swap. You have both a cationic and anionic complex ion, and the ligands can switch places between the two.
So it's a molecular square dance, with the ligands changing partners.
You got it. Imagine a cobalt complex with ammonia ligands and a chromium complex with cyanide ligands. In a coordination isomer, the ammonia ends up with chromium, and the cyanide goes with cobalt.
Okay, it's a molecular switcheroo. What about ionization isomerism? How is that different?
Ionization isomerism is similar, but instead of swapping ligands between those complex ions, a ligand swaps with a counterion. It's like someone outside the dance floor suddenly jumps in and switches places with one of the dancers.
A bit less dramatic, but still a partner swap.
Exactly. For example, imagine a cobalt complex with a bromide ligand inside and a sulfate ion outside. In an ionization isomer, the sulfate would move inside the complex and the bromide would be outside.
Okay, I'm starting to see the patterns here. What about that last type of structural isomerism, the one where solvents get involved?
Ah, yes, that's solvate isomerism, or hydrate isomerism if water is the solvent. It all depends on whether a solvent molecule is directly bonded to the metal ion, or if it's just hanging out nearby as a free solvent molecule.
So some solvent molecules are VIPs, invited inside the coordination sphere, while others are left out in the cold.
That's a great analogy. One classic example is the chromium chloride complex. There's a violet version where all 6 water molecules are bonded to the chromium ion, and then there's a gray-green isomer where only 5 water molecules are bonded, and one's off doing its own thing.
So the location of that one water molecule actually changes the color of the compound.
It does. It really highlights how even those seemingly small changes can have a big impact.
This is making me even more curious about stereoisomers. Those are the ones where the bonds stay the same, but the arrangement in space makes all the difference, right?
You've got it. Think of it like rearranging furniture in a room. You're not changing the furniture itself, but how it's arranged impacts the overall look and feel.
Okay, that's a helpful analogy. So how many ways can we rearrange these molecular furniture pieces?
Let's start with geometric isomerism. This is all about the positions of the ligands around the metal ion. In square planar complexes, you've got those classic cis and trans isomers where ligands are either on the same side or opposite each other.
Like 2 lamps on either side of a bed.
Exactly. And octahedral complexes can also have cis and trans isomers, but we also see FAC and MER isomers.
FAC and MER, I'm intrigued.
FAC stands for facial, and MER stands for meridional. Imagine the octahedral complex as a globe. In the FAC isomer, 3 identical ligands are clustered together on one face, like a triangular continent. The MER isomer has those 3 identical ligands arranged around the meridian of the octahedron, like a line of longitude.
Okay, I'm picturing that. So FAC is like a group of friends huddled together, and MER is like a line of dancers in a conga line.
Perfect analogy, and just like with cis and trans, these arrangements create distinct properties for the complex. Now, ready for the grand finale of isomers.
Hit me with it.
Optical isomers, these are like mirror images of each other.
Ah, I remember these from organic chemistry. They're like your left and right hand. They look the same, but they're not superimposable.
Exactly. We call these isomers enantiomers, and molecules that exhibit this property are called chiral.
So it's all about having different groups attached to the central atom, giving it a handedness. What makes these optical isomers so special?
They interact with polarized light in a very particular way.
Like the light that comes through sunglasses.
Similar, polarized light only vibrates in one plane, and these chiral molecules rotate the plane of polarized light as it passes through.
Wow, so they're like tiny little light twisters.
Pretty much. And this property is super important in biological systems because many biological molecules are chiral.
So their handedness affects how they function in living organisms.
You got it.
Okay, my mind is officially blown by the world of isomers. But let's zoom out for a moment and think about how those bonds actually form.
To understand those bonds, we have to delve into the theories that explain how these metal ions and ligands get together.
Okay, lead the way. I'm ready for another theoretical adventure.
Let's start with valence bond theory. VBT for short.
Okay, VBT. What's the basic idea?
It's all about those atomic orbitals and how they overlap. When they do, they form a covalent bond.
So it's like two atoms deciding to share their personal space.
Yeah, and in the case of coordination compounds, VBT says that metal ion is using its empty orbitals to accept those electron pairs from the ligands.
So it's like the metal ion is offering up some empty rooms, and the ligands are bringing in their luggage full of electrons.
Exactly. Everyone benefits. And you might recall from chemistry class that those orbitals can hybridize.
Oh yeah, hybridization.
Yeah,
Does that happen in coordination compounds too?
absolutely. It's a key part of VBT. The metal ion mixes up its atomic orbitals, creating those new hybrid orbitals, and then those overlap with the ligand orbitals. That's how we get those coordinate covalent bonds.
So the metal ion is doing a little rearranging to make space for the incoming ligands.
You got it. And the type of hybridization determines the geometry of that complex, whether it's octahedral, tetrahedral, or square planar.
So hybridization is like the architect of the coordination compound, shaping its overall structure. But you mentioned earlier that VBT has some limitations. What are those?
Well, one thing VBT doesn't always predict accurately is the magnetic properties of some complexes.
What do you mean by that?
It can't always tell us whether a complex will be attracted to a magnet or repelled by it.
So it's like VBT can't always tell us if a complex is magnetically friendly or not.
Exactly. And that's where crystal field theory, or CFT, steps in.
Okay, CFT, bring on the insights. What's his perspective?
CFT shifts the focus. It's all about those electrostatic interactions between the metal ion and the ligands, attraction and repulsion between those charges.
Okay, so instead of focusing on the steps of the dance, CFT is zooming out to look at the energy between the partners.
Exactly. It simplifies things by imagining those ligands as point charges. And it focuses on how these point charges affect the energy levels of those d orbitals in the metal ion.
The d orbitals. Weren't those the ones involved in bonding?
You bet. In a free metal ion, all 5 d orbitals have the same energy. But when those ligands come into play, their electric field splits those d orbitals into different energy levels.
It's like the ligands are setting up an energy obstacle course for the d electrons.
I like that. And how those d orbitals split depends on the geometry of that complex. In an octahedral complex, for example, they split into 2 groups, a lower energy group and a higher energy group.
So it's like the d orbitals are in a limbo contest, and the ligands are setting the bar.
Exactly. And the energy difference between those groups is called the crystal field splitting energy.
That sounds important. Does it impact the compound?
Oh, it's a key factor in determining color and magnetic properties. It even helps us understand why some complexes are high spin, meaning their electrons are spread out, while others are low spin, with those electrons paired up.
So the crystal field splitting energy is the choreographer of the electron dance, telling them how to arrange themselves.
That's a great way to put it. Now, CFT is powerful, but it has its limitations, mostly because of that simplification of ligands being just point charges.
Right, because in reality, those ligands have their own shapes and personalities.
Precisely. That's where more advanced theories come in, like ligand field theory and molecular orbital theory. They give us a more nuanced picture. But for many purposes, VBT and CFT provide a good foundation.
Okay, so I've got a better understanding of those bonds now. But let's shift gears and talk about the real-world impact of these compounds. You mentioned that they're involved in things like photosynthesis and purifying metals. Can you give us more details on that?
Absolutely. We talked about chlorophyll and hemoglobin already. But coordination compounds are also crucial for many enzymes. You know, those biological catalysts that speed up chemical reactions.
So they're like the pit crew of the biological world, keeping those enzymes running smoothly.
That's a perfect analogy. And those enzymes are involved in a huge number of processes, everything from digestion to DNA replication. Without coordination compounds, life as we know it just wouldn't exist.
Okay, that's incredible. But what about applications beyond biology? What about industry and technology?
Oh, they're incredibly versatile. In medicine, for instance, we use these special ligands called chelating agents to remove heavy metals from the body.
It's like a molecular detox for heavy metal poisoning.
Exactly. And in industry, they're key players in catalysis, in extracting metals, even in electroplating.
Okay, I'm seeing a theme here. Coordination compounds are like the unsung heroes of the chemical world, quietly making our lives better.
That's one way to put it. They really are everywhere. In fact, let's take a trip back in time to the days of black and white photography. Have you ever wondered how those classic photos were developed?
Oh, absolutely. It's always seemed like darkroom magic to me.
Well, there's definitely some chemistry involved. When you snap a black and white photo, that film is coated in silver bromide. It's sensitive to light.
Okay, so the light hits the film. What happens then?
When the light hits the silver bromide, it creates what we call a latent image. a hidden picture, just waiting to be revealed.
It's like a molecular treasure map.
Exactly. And to develop that image, we use a special solution, a developer, that contains a reducing agent. This reducing agent does the magic, converting those silver ions in the silver bromide into metallic silver.
So it's like a magic potion that brings the image to life.
That's a great way to put it. But we're not done yet. After the image is developed, we have to get rid of all that unexposed silver bromide. Otherwise, the photo keeps getting darker.
So how do you stop it from darkening?
That's where another solution comes in called the fixer. This one contains sodium thiosulfate. It reacts with the unexposed silver bromide and forms a soluble complex ion.
So the fixer is like a molecular eraser, cleaning up all that unwanted silver bromide.
Precisely. And since that complex ion is soluble, we can just wash it away, leaving behind the developed image.
Wow, so this seemingly simple process of developing a photo actually relies on the unique properties of a coordination compound. It's like a chemical collaboration to create those lasting images.
It is, and it's just one example of how coordination chemistry is working behind the scenes, making things happen that we might take for granted.
Okay, that's a fascinating example from photography. What about something from the environmental world? Are coordination compounds helping us protect our planet?
Absolutely. They're playing a crucial role in wastewater treatment. You see, wastewater can contain all sorts of nasty stuff, heavy metals, organic compounds, excess nutrients. It's a real mess.
So coordination compounds are like the cleanup crew, tackling that pollution.
Exactly. And they do this in a few ways. One way is through precipitation, basically creating a molecular net to trap those pollutants and pull them out of the water.
So it's like fishing for pollutants with the right kind of bait.
Perfect analogy. And coordination compounds can also be used in adsorption processes, ion exchange, even in advanced oxidation processes that break down those stubborn organic pollutants.
Wow, so they're like a whole army of molecular cleaners, tackling pollution on multiple fronts. This is making me think about material science. Are coordination compounds used in creating new and innovative materials?
You bet. One area where they're really shining is in the development of metal organic frameworks, or MOFs for short.
MOFs. Those sound futuristic.
They kind of are. Imagine them as molecular sponges.
Sponges.
Yeah. They're porous, meaning they have lots of tiny holes, and they can trap specific molecules.
So they're like molecular sieves, selectively filtering out certain substances. What can we use them for?
Oh, they have tons of potential applications, everything from gas storage and drug delivery to catalysis.
Okay, slow down. How do they work for gas storage? Are they like tiny molecular storage tanks?
Exactly. They can hold a lot of gas in a small space. So we're talking potentially storing hydrogen for fuel cells or even capturing carbon dioxide from the atmosphere.
So tackling both the energy crisis and climate change. Impressive. What about drug delivery? How do MOFs help with that?
Well, we can design these MOFs to release drugs in a very controlled way, delivering them directly to the target site in the body.
So it's like a molecular FedEx, getting that medicine exactly where it needs to go. And you mentioned catalysis too. How do they help with that?
MOFs have a huge surface area, all thanks to their porous structure. So there's tons of space for catalytic reactions to happen. Plus, the metal ions in those MOFs can act as active sites, really speeding things up.
So it's like a molecular factory with lots of space for workers and specialized equipment to get the job done efficiently. It sounds like these MOFs are the molecular multitaskers of the future.
They truly are. And this is just one example of how coordination compounds are pushing the boundaries in material science. But with any powerful tool, there are potential downsides, right?
That's a good point.
Yeah.
It's important to remember that every innovation comes with responsibility. What are some potential risks we need to be aware of with these compounds?
Well, toxicity is definitely a concern. Some coordination compounds, particularly those involving heavy metals, can be harmful to living things.
So it's like some of those molecular superheroes have a dark side if they're not handled properly.
Exactly. We have to be careful and responsible, making sure they're disposed of properly and keeping an eye on their levels in the environment.
Right. It's all about using our knowledge to harness their power while minimizing any harm. What other concerns are there?
Another issue is bioaccumulation. Some of these compounds can build up in the tissues of living organisms over time, and if they're toxic, that can lead to problems down the road.
So it's like they're overstaying their welcome.
Precisely. And there's also the potential for them to form in ways we didn't intend. Sometimes metal ions in the environment react with ligands from various sources and form coordination compounds that have unpredictable effects.
So it's like an unplanned molecular party, and we don't know what might happen.
That's a great way to put it. These unexpected compounds can affect things like soil fertility and pollutant mobility.
Okay, so it's a balancing act, appreciating the amazing potential of these compounds while being mindful of the risks.
Exactly. Understanding the chemistry is key to using them wisely.
This deep dive has been eye-opening. Coordination compounds are clearly more than just textbook examples. They're crucial to our world. And I have to admit, you've really ignited my curiosity about them.
Well, that's what I love about this field. There's always more to explore and discover.
Now, I'm really curious about your personal journey in this field. What drew you to coordination chemistry? What sparked your passion for these intricate molecules?
It was a few things that came together. I've always been fascinated by the molecular world, but with coordination compounds, it was the challenge of understanding these complex systems, how those metal ions and ligands work together to create those unique properties.
So you were drawn to the intellectual puzzle of it all. What keeps you engaged and excited about this field?
For me, it's realizing that these compounds aren't just theoretical curiosities. They have a real impact on our world. They're essential for life, they're used in medicine and industry, and they're key players in solving some of our biggest global challenges.
So it's that potential for making a positive impact that fuels your passion.
Absolutely. And I'm always inspired by all the new discoveries and innovations in this field. It's constantly evolving and pushing the boundaries of what's possible.
Your enthusiasm is contagious. I'm starting to feel that same excitement about exploring this field further.
I encourage you to do it. There's a whole world waiting to be discovered.
This deep dive has been an amazing journey. We've covered so much ground, from the history and structures to the applications, the beauty, and even the potential risks of coordination compounds.
It's been a great conversation. I'm glad we could delve into these fascinating molecules together.
And I know our listeners are feeling just as enthralled as I am by the world of coordination chemistry. They're more than just textbook examples. They're a testament to the creativity and beauty of chemistry.
I couldn't agree more. They really do showcase the elegance and power of the molecular world.
Now, before we move on to some cutting-edge research and the future of coordination chemistry, I'm curious, are there any common misconceptions or myths about these compounds that you'd like to clear up?
Absolutely. Coordination compounds often get a bad rap for being too complex or obscure. That leads to some misunderstandings about what they are and why they matter.
Okay, let's bust some myths. What are some of the most common misconceptions you encounter?
One big one is that coordination compounds are purely synthetic, that they don't exist in nature.
So people think they're just lab creations.
Exactly. But as we've seen throughout our deep dive today, coordination compounds are absolutely essential for life. They're all over the place in plants, animals, and the environment.
Right. Chlorophyll, hemoglobin, enzymes. We wouldn't be here without them.
Precisely. They're not artificial constructs. They're fundamental parts of nature's design.
Okay, myth busted. What's another misconception you hear often?
Another common one is that all coordination compounds are brightly colored.
I can see why people might think that. Those gemstones are pretty dazzling.
Yeah, but while some are definitely vibrant, many are actually colorless. The color depends on the electronic structure of that complex, which is influenced by the metal ion, the ligands, and the geometry.
So it's not a one-size-fits-all situation. Their color can vary just like any other property.
Exactly. And another misconception is that all coordination compounds are super stable.
So people think they're like unbreakable molecular fortresses.
Yeah. But in reality, stability depends on a lot of things. The strength of those metal ligand bonds, the nature of the ligands, the surrounding environment.
So context matters. What about toxicity? Is there a misconception that they're all dangerous?
That's another common fear. And while some coordination compounds are toxic, many are perfectly harmless. The toxicity really comes down to the specific metal ion, the ligands, and the structure of that compound.
So we can't just lump them all together. We have to look at each one individually. What about misconceptions surrounding the field itself, the study of coordination chemistry?
One that I hear a lot is that coordination chemistry is purely theoretical, that it has no real-world applications.
So it's all equations and models, no practical use.
That's the misconception. But, as we've discussed, coordination compounds are everywhere in practical applications. Medicine, industry, material science, environmental chemistry, the list goes on.
We've barely scratched the surface with all the examples we've talked about today, from photography and wastewater treatment to drug delivery and nanotechnology.
Exactly. Coordination chemistry is incredibly practical. It's about solving problems, creating new technologies, and understanding the world at a molecular level.
Okay, so we've busted some myths and highlighted the incredible importance and versatility of these compounds. But what about the future? What's on the horizon for coordination chemistry?
Oh, that's a great question. This field is incredibly dynamic, and researchers are constantly pushing the boundaries. There are so many exciting new directions emerging.
Okay, give me a glimpse into the future. What are some of the cutting-edge areas of research that are creating a buzz?
Well, one area that's really hot right now is supramolecular chemistry.
Supramolecular chemistry, what's that all about?
Think of it as coordination chemistry on a larger scale. Instead of just single compounds, we're talking about assembling those molecules into larger, more complex structures.
So it's like building molecular skyscrapers using coordination compounds as the bricks.
Exactly. And what's really cool is that these supramolecular assemblies are held together by these weaker interactions like hydrogen bonding and van der Waals forces.
So it's more like the molecules are holding hands rather than sharing electrons.
Yes. And supramolecular chemists are creating these incredible architectures, things like molecular cages, capsules, even molecular machines and sensors.
Wow, that sounds like something out of science fiction. What could we even use those for?
Oh, the potential applications are huge. We're talking about revolutionizing fields like drug delivery, catalysis, sensing, and materials science. Imagine molecular machines that can deliver drugs directly to diseased cells or sensors that can pick up tiny amounts of pollutants.
So it's like coordination chemistry is providing the building blocks for a whole new world of molecular devices and systems.
That's a great way to put it. And another area that's really exciting is bio-inorganic chemistry.
Bio-inorganic chemistry, what's that all about?
It's all about the role of metals in biological systems. Things like how enzymes function or how cells communicate.
So it's like investigating those metal ions that are partying inside biological molecules.
Precisely. And this research is giving us new insights into diseases and new ways to develop treatments.
Okay, those are some fascinating frontiers in coordination chemistry. What about more specific applications? Are there any new and exciting ways that these compounds are being used?
Oh, absolutely. Nanotechnology is a great example. Coordination compounds are being used to create all sorts of new nanomaterials with unique properties.
Nanotechnology, that's the science of the super small, right?
Exactly. And one way these compounds are being used is in creating nanoparticles.
Nanoparticles, those tiny particles with amazing properties, what are they doing there?
Well, nanoparticles typically have dimensions less than 100 nanometers, and they have these unique optical, electronic, and magnetic properties that make them incredibly versatile.
So how do coordination compounds fit into all of this?
One approach is to use them as precursors for making nanoparticles. We can design these compounds to break down under certain conditions, releasing those metal ions that then form the nanoparticles.
So it's like using a molecular mold to shape and control those nanoparticles.
That's a great analogy. And by tweaking the conditions, we can really fine-tune the size, shape, and composition of those nanoparticles.
So coordination compounds are like the architects of these tiny but powerful nanomaterials. What other nanotechnological applications are there?
Another really exciting area is the development of molecular machines.
Molecular machines, you mean like tiny robots made of molecules?
Exactly. It does sound a bit like science fiction, but thanks to advances in coordination chemistry, we're getting closer to making these machines a reality.
So coordination chemistry is providing the nuts and bolts for these nanoscale devices. What could we even do with them?
Oh, the possibilities are mind-blowing. We could revolutionize things like medicine, energy, and materials science. Think about targeted drug delivery systems, self-healing materials, even new diagnostic tools.
Okay, my head is spinning with all these potential applications. It's clear that coordination chemistry is at the forefront of some incredible technological advancements. But with any new technology, I imagine there are challenges to overcome.
You're absolutely right. There are definitely challenges that researchers are tackling in this field.
Like what? What are some of the biggest hurdles facing coordination chemistry?
Well, one challenge is the sheer complexity of these systems. We're talking about multiple metal ions, a huge variety of ligands, and intricate three-dimensional structures.
So it's like solving a multi-dimensional puzzle with pieces that keep changing.
Exactly. It takes really sophisticated techniques and advanced models to understand how these complex systems work.
It's definitely not for the faint of heart. What are some other challenges in this field?
Another big one is controlling reactivity. Coordination compounds can be quite reactive, and sometimes it's hard to predict and control what they'll do.
So it's like trying to tame a molecular wildcat. need to harness its energy without getting scratched.
I love that analogy. Controlling reactivity is key if we want to develop new applications. Whether it's designing a catalyst for a specific reaction or creating a sensor that responds to a particular molecule, we need to be able to control the reactivity.
So it's about finding that balance between understanding their inherent reactivity and finding ways to direct it in a predictable way.
Precisely. And another challenge is synthesizing new compounds. Making a coordination compound with specific properties can involve a lot of steps and require specialized equipment.
So it's like a molecular chef trying to create a new dish, experimenting with different ingredients and techniques to get the flavors just right.
That's a great way to think about it. Chemists are always coming up with new synthetic strategies, looking for ways to create compounds with novel structures and properties. They're constantly expanding the toolbox for different applications.
Okay, so despite the challenges, there's still a ton of excitement and innovation happening. Scientists are constantly pushing the boundaries and finding new ways to unlock the potential of coordination compounds.
Absolutely. And those challenges are part of what makes this field so dynamic and rewarding.
Well, I'm excited to see what breakthroughs emerge in the future. But before we get to that, I think it's important to take a moment to appreciate the beauty and wonder that coordination chemistry reveals.
I agree. Coordination compounds are more than just formulas and reactions. They offer a glimpse into the elegance and artistry of the molecular world.
Okay, I'm ready for a moment of molecular appreciation. What are some examples that showcase that beauty?
Well, let's go back to those dazzling gemstones we talked about earlier. Those vibrant colors are a direct result of coordination compounds.
Right? Emeralds, rubies, sapphires. They're like nature's own works of art.
Exactly. The metal ions in those gemstones are surrounded by ligands, and their interaction with light creates those breathtaking colors. Each gemstone has its unique color signature, all thanks to coordination chemistry.
It's amazing how something so small, the arrangement of atoms, can create something so visually stunning.
It is. And another example of that molecular beauty is in the structures of those MOFs. Remember those porous coordination polymer?
Oh, yeah, the molecular sponges with those intricate pores.
Scientists are creating MOFs with a huge range of shapes and sizes, everything from simple cubes and spheres to these complex networks and honeycombs.
It's like molecular architecture, building structures that are both beautiful and functional.
Exactly. It's a reminder that beauty and functionality can often go hand in hand, even at the molecular level.
Okay, you've convinced me. I'm adding appreciate the beauty of coordination compounds to my to-do list.
I highly recommend it. It's a great way to connect with the wonder of chemistry.
This deep dive has been incredibly inspiring. Coordination compounds are complex, diverse, and essential for life. They're like those hidden architects, shaping our world in ways we never imagined.
I couldn't agree more. It's been a real pleasure discussing this fascinating topic with you.
And I know our listeners are feeling just as captivated as I am by the world of coordination compounds. They're not just textbook examples. They're a testament to the creativity and beauty of chemistry.
Absolutely. They remind us that the molecular world is full of wonder and endless possibilities.
Now, before we wrap up this deep dive, I have one final question for you. If you could leave our listeners with one lasting thought or takeaway, what would it be?
I think the most important takeaway is to remember the interconnectedness that coordination chemistry reveals. It bridges the gap between the inorganic and organic worlds, showing us how different areas of chemistry come together and impact our lives.
So it's about more than just molecules and reactions. It's about seeing the connections, the possibilities, and understanding how everything is woven together.
Exactly. It reminds us that the world is more interconnected than we often realize, and that even the smallest things, like the interaction between a metal ion and a ligand, can have a profound impact on the bigger picture.
That's a beautiful and inspiring way to end our exploration. Thank you so much for joining us on this deep dive into the world of coordination compounds.
It's been my pleasure.
And to our listeners, thank you for tuning in and for your curiosity about the molecular world. Keep exploring, keep asking questions, and keep discovering the wonders that chemistry has to offer. So we've explored the vast world of coordination compounds, their structures, their bonds, their applications, even their potential downsides. But now I'm curious about your journey into this field. What was the aha moment that ignited your passion for these compounds?
Well, for me, it was a perfect storm of fascination. I was always drawn to the intricate beauty of the molecular world, but coordination compounds just took it to a whole other level. Those vibrant gemstone colors, the intricate structures of MOFs. It was like discovering a hidden whistle of art, but at a molecular scale.
So you're a chemist with an artist's eye.
Maybe a little bit. But beyond the aesthetics, it was the intellectual challenge that really captivated me. These compounds can be so complex with multiple metal ions, all those different ligands, and those fascinating 3D structures. It's like a never-ending puzzle, trying to understand how all the pieces fit together and how those interactions create such unique properties.
So beauty and brains, the perfect combination. What keeps that passion burning bright after all these years?
You know, as I delve deeper into this field, I realize that it's not just about pretty structures or challenging puzzles, it's about real-world impact. Coordination compounds are essential for life itself. They drive a vast range of technologies, and they're playing a key role in tackling some of the world's biggest challenges, like climate change and sustainability.
So you're driven by the potential of coordination chemistry to make a positive difference.
Absolutely. Knowing that my research could contribute to developing new medicines, cleaner energy sources, more sustainable materials, that's what keeps me going.
Well, your passion is definitely contagious. I've gained a whole new appreciation for these compounds and the field that studies them, thanks to you.
It's been my pleasure to share my enthusiasm for coordination chemistry.
This deep dive has been an incredible journey, from history and structures to applications, beauty, and the future of these fascinating compounds. It's clear that coordination chemistry is vibrant, dynamic, and brimming with potential.
I couldn't agree more. It's a field that never stands still, always pushing the boundaries with new discoveries and breakthroughs.
As we wrap up this exploration, I'd like to ask, what's one final thought or takeaway you'd like to leave our listeners with?
I'd say look at the world around you with a renewed sense of wonder. Coordination compounds are everywhere, silently shaping our lives and impacting the world in ways we often don't even realize.
So it's about appreciating that hidden chemistry that's happening all around us, from the colors of a sunset to the way our bodies function.
Exactly. Coordination chemistry shows us that the world is full of wonder and complexity. Even the tiniest interactions, like those between metal ions and ligands, can have a huge impact on the bigger picture.
That's a beautiful and inspiring message to end on. Thank you so much for joining us on this deep dive into the world of coordination compounds.
The pleasure was all mine.
And to all our listeners, thank you for tuning in and for your curiosity about the molecular world. Keep exploring, keep asking questions, and keep marveling at the wonders that chemistry has to offer.